Hello, I think we are live. Just make sure we're all set up here with the chat. All right, hopefully everyone can hear me. Welcome to our third ever live stream, which is on the topic of how to deploy a Django app to Kubernetes. And it's a follow-on from the last live stream which we did, which was how to deploy Django to Kubernetes, but we did that on our local machine using Minikube. So we set up a project and a configuration and everything to run Django on our local machine using Minikube. But don't worry if you didn't take that, because we're going to provide the starter code so you can just kind of pick up where we left off and follow along if you want to follow along and you didn't attend the last live stream. So what we did in the last live stream is we put a survey out where we asked people what they wanted us to deploy to, and the most popular one was AWS. So that's the one we went with. Before I continue on with this presentation that we've created here, there's a few requirements that you might want to have installed, so I just want to get them out of the way first. So if you haven't got them installed, you can go ahead and install them. I did list them in the description of this video, along with the links to where you can download each thing. So what you're going to need to follow along is an AWS account. You're going to need an IAM user or authentication with that account, so you can authenticate with the local command line interface, so that you can run the commands and make changes to AWS. You're going to need Docker installed, Terraform, AWS Vault, which is kind of optional. That's the way that I like to authenticate my local AWS command line interface with AWS. If you don't use AWS Vault, then you can just use the environment variables or the AWS single sign-on command that comes with the AWS CLI. But I recommend AWS Vault. It's a really nice way to manage your credentials in a secure way that lets you keep them in an encrypted store on your machine as opposed to just plain environment variables. You also want the AWS CLI. Again, there's links in the description to where you can download and install each one of these things. They should be relatively straightforward to install, and they all should be available for both Windows and Mac OS. And the Kubernetes CLI, so that's the kubectl command line tools. And Helm. Helm is like a kind of like a configuration manager for Kubernetes. Someone actually asked about it in the last live stream, and it turns out that we do actually need to use it, and we can actually use it to save quite a bit of time in this live stream. So thank you for the suggestion, thank you for the request. So we'll just give it a few minutes while you go ahead and install that. Just quick shout out to Brooke, who is doing the moderation of the comments. So if you have any comments or questions, or there's any technical issues or anything like that, please put them in the comment, and then Brooke will make sure they get passed to me if I don't see the message myself. So basically, here are the results from the survey. So the survey that we put out from the last live stream, which asked which platform would you like us to deploy to. Basically, the number one by far was AWS. So you can see that AWS has more than all the others combined. And that makes sense because it is probably the most used cloud provider that's out there. And yeah, it's the most used by businesses. So we figured that people probably want to follow these streams and learn this stuff because they want to apply it to work, to their jobs. And most people's companies probably use AWS in most instances. But the good thing about Kubernetes is it is used, or can be used, on basically all of the major cloud platforms. A lot of the stuff that you learn will be applicable to other cloud platforms, and maybe in the future we'll do some other live streams related to other platforms. But for now, because it was by far the most popular, we're definitely going to stick with AWS. The upside of using AWS is, as I was saying, it's the most mature platform, so it's kind of been around the longest, or at least it's the most it's got the most mature set of resources that are available for it. It's reliable, it's used by many corporations and governments all over the world, and it has numerous integrations. They have like such a vast library of different resources and different things that are available. It's quite easy to get lost in AWS because of how many different resources are available, and it is by far the most popular in the industry. If you look at any of the data and surveys and things like that, it's the most used platform. The downside to using it is that it's quite expensive, and this is really the only downside, particularly when it comes to using Kubernetes. And that was why I was initially hoping to do it using a different platform that was more affordable, because I figured that not everyone can afford to spend lots of money on hosting resources. But since everyone in the survey wanted to go with AWS, we're going to do this one in AWS, and I've made some specific adjustments to this to try and keep the costs low. Of course, everybody is obviously responsible for their own costs and doing their own calculations and stuff like that. But yeah, that's really the only downside, is that it's one of the most expensive ones, but it is a very powerful platform. So the rough costs, this is just the rough costs. As I was saying, everyone's responsible for their own AWS costs and doing their own calculations. But roughly, this whole deployment would cost approximately $132 a month to run, or that's almost $1,600 a year. As I was saying, it is one of the most expensive ways that I see to run Kubernetes in the cloud. However, they do offer the most powerful set of resources, so it does have a lot of benefits, and that's why lots of companies like to use it. And this, of course, is just a rough estimate, and this is kind of keeping everything to the minimum that I could. So we're going to use the minimum number of EC2 resources. As you can see, that's 1723. They charge $73 per month just to use the Kubernetes control plane, which was a bit of a surprise to me, because a lot of the other cloud platforms like Linode or DigitalOcean, they actually offer that for totally free. So the control plane doesn't cost any money. It just costs money to actually run the virtual machine nodes that the control plane manages. But Amazon, it's available across multiple availability zones, and it will be one of the most reliable ways to run Kubernetes. So I think that's why they can justify the cost, because they do it in quite a reliable way that has lots of, it doesn't have any single point of failures and stuff like that. So yeah, just to run Kubernetes, the base cost is $73, and then you need to pay for the EC2 instances. So using one of the cheapest instances, it's $17. And then we're going to use RDS, because it's quite challenging to deploy Postgres, or I couldn't get Postgres working on a Kubernetes image with a good persistent data storage. Maybe we'll talk more about that later, but I think I recommend using RDS for the database backend if you're going to deploy anything, instead of trying to get Postgres to work inside Kubernetes. And then we got Elastic File System, which is the persistent storage, the persistent data that we use. Is quite cheap, actually. We're only using, I think, 5 gigabytes. So it's quite low cost. Obviously, that cost increases the more you use it. And then you've got the Elastic Container Registry, which again is a negligible cost, like $2-3, and that's with, I think I put 10 gigabytes of transfer per month, which is probably more than you would need. But it might be less than you need. Again, it all depends on your use case. I recommend going to the AWS cost calculator and doing a full calculation before you go ahead and actually start creating resources, because otherwise you might be surprised with the costs. But that's one of the reasons why I wanted to use Terraform for this, because with Terraform, what we can do is we can create the resources just for this live stream. You can play around with it, test it out, and then as soon as the live stream's done and you're not working anymore, you can destroy all of the resources and no longer be paying the fees. So that's the way that I've been developing this live stream when I've been testing it out. I've been using Terraform to spin up the resources. You get charged for what you use per minute, and then you spin it all down at the end of the day, and then you don't need to get charged when you're not using it. Now, obviously, if you need the deployment running 24/7 for a real app, then it's a bit different. You do need to have it running. But for the purposes of learning, Terraform is really useful, and it provides a great cost saving to this, because you don't need to remember to, well, you need to remember to destroy the Terraform, but you don't need to remember to go into the console and delete every single resource individually. Okay, so let's just quickly go over what we'll be doing. So we're going to be deploying Django to Elastic Kubernetes Service, or EKS. And we're going to use Terraform to define the architecture so we can easily create it and destroy it, again, for that cost-saving benefit. And we're going to use Elastic File System to store the static data. There's different ways you can store static data. Elastic File System is one of the most powerful because it allows you to mount onto many different nodes in read and write mode. So you could scale up your application, you could have hundreds of nodes, and you could mount them all to the same Elastic File System and that will allow you to have the most scalability. And it's also very reasonably priced, and it costs, as long as you don't have too much data on there, it doesn't cost too much. So yeah, just the read write many. This is one of the things with Kubernetes is most of the file system backends only support read write once, which means that one node can write at a time. So this can sometimes be an issue if you're trying to scale, because you might want to have 10 nodes running your application and you want all requests to that application to be able to write to the file system. Whereas if you're using many of the different default file system backends, you can't do that. Whereas EFS was the only one that I found on Amazon that is provided as an Amazon service that allows you to do that very easily. We'll also be installing this EFS driver onto our Kubernetes cluster using Helm to save us a bit of time, and this is the recommended way they suggest to do it on the documentation. We'll be using RDS for the database. Again, I tried to fight with Postgres on Kubernetes for ages, and it didn't seem to like the file permissions that come with EFS and the way that it's set up, and I gave up in the end. If anyone does know how to do that, then please let me know. But I thought the most straightforward approach, and probably the one that most people want to use nowadays, is to use the hosted RDS service on AWS, because it's very powerful. They manage all the updates for you and stuff like that. I'm sure you could get Postgres running inside AWS if you want, but most cloud providers do provide some kind of Postgres hosted service, which is probably easier from a maintainability standpoint. Okay, so that is everything we're going to be doing. Let's just dive right into it. Okay, so we did provide some starter code, which is in the description of this video. So there's two kind of projects: the AWS Django EKS tutorial starter. This is the baseline code that we're going to be starting with. And then there's another project, which is the same name, but without starter at the end. This is the finished code. So this is everything we're going to be doing step by step. I actually put each step as a separate branch here, and we're going to be working through to create this. I also put in the README file a lot of the, or a link to all of the requirements that you need, as well as some of the more complicated commands. So if you're struggling to follow along reading on the screen, you can head over to this repository here. So that's under London App Developer /AWS Django EKS tutorial. And you can copy and paste them from here, and it might be easier for you to do it that way than to try and type it out. So yeah, this is really just for your convenience. We're going to be going through and talking through what each of these do as we progress. Okay, so the first thing that we're going to do is we're going to initialize Terraform in our project. So I presume you have Terraform installed and you have an AWS account set up with your AWS authenticated. So we can load up this, and I use AWS Vault. So AWS Vault exec, then the name of my profile, and then I make it valid for 8 hours because probably going to be using this for most of the day. And this will allow me to run Terraform against my AWS account. Okay, so what we'll do first is we'll head over to the starter code, and I'm going to download this. So just because I wanted to make sure I'm starting from exactly the same place that all of you guys are starting from as well. So I'll download this into my workspace here, and I'm just going to extract, if I can find my Finder. Okay, so we're going to extract this here. We'll call this AWS Django EKS. Okay, and what I might also do is create a quick project here for you to follow along if you need to kind of catch up to where we are. Actually, I need to do that in my other account. So let's do that here. So we'll call this one AWS Django EKS tutorial live. Okay, actually, we won't do that. We'll put it in the demo account. Sorry, again, confused myself here. So I have a demo account here. It was AWS Django EKS tutorial. And I'll make this public, create a repository. Okay, so if I go to workspace, go to the latest one, which is AWS Django EKS, and that's the one I just extracted. So I'm going to initialize this as a project, and we're going to push it up here. So just do git commit. git add, git commit, initial. And I'm going to add the remote here, and then the branch as main, and then we're going to push this. Okay, so this is the kind of project as we go along. I'm going to share this in the chat in case you need access to it. So if you want to just catch up to where we are, then you can just jump to this and pull the latest. I'll push it up to Git as we go along. Okay, great. So the first thing we're going to do is set up Terraform. So I'm going to open up this project, and I like to put all of my Terraform code in a subdirectory called infra, short for infrastructure. And in main.tf is the kind of main module that we're going to use. We're also going to use the Terraform git ignore. So you can either find in the resources, or you can just go Terraform git ignore on GitHub, and it should come up here. So we're going to use this because we're going to be committing Terraform to our project, and we don't want them to commit the files that aren't supposed to be committed. I'm also going to add DS store, which is just Mac specific things here. Stop them popping up. And paste in my Terraform configuration, or my Terraform git ignore. And then we're going to open up main.tf, and in main.tf, we are going to add the following. So we're going to start by creating the Terraform block here. So Terraform, and then required providers, and these are the providers that we need for our Terraform. So AWS source equals HashiCorp /AWS. And then version equals, we're going to be using the version 4.67.0. This just ensures that we're using the right provider version. And then provider AWS region equals var.region. And we're going to add another file. So we'll save that. We'll add another file called variables.tf, where we define the region. And that is going to be description equals AWS region to deploy resources to, and default equals EU West 2. So I'm closest to London, so I'm using the EU West 2 one, which is based in London. I have the auto formatting enabled, so when I save the file, it uses the Terraform format command to auto format. If you want to do that yourself, you can run Terraform FMT, and it will do that for you. Okay, so that's done. Now we just need to do Terraform init to initialize. And I have an error here already, so provider is not supported. I think I put a typo here. Yeah, so provider is meant to be outside of the Terraform block, like that. And underneath here, you can actually put required version to say what is the version of Terraform you want to use, just so you know you're not upgrading the state in the background. It's just kind of a best practice thing. So I have the Terraform version installed that I listed there. So it's 1.4.6. So basically what this does is when you run it, it pulls down the provider and everything that's needed. And we're going to be running that init command quite a few times along the course of this tutorial. Okay, so that's everything for the first step. So what we could do is commit that, git commit, added, let's say added Terraform config. Did that not commit? Oh, did it from the wrong directory, I think. All right, so now we'll push that up. So if you needed to pull that down, then you could do that yourself. Okay, so we've set up Terraform. The next thing we're going to do is create a VPC. And the VPC is going to be the kind of back end for our entire network that our Kubernetes runs on. So we're going to create in infra here vpc.tf. And we'll do data. Actually, no, we'll do inside main.tf, we're going to add a new line called data. AWS availability, see if I can spell this, zones available. And all this does is it provides a data provider that lets us know what all of the zones are that are available in our authenticated AWS account. And then inside vpc.tf, we are going to add the following. So we are going to create our VPC, and we're going to use a module for that. So modules basically are kind of like a predefined modules that people have created and published on Terraform that allow you to do things easier than if you were creating all of the resources themselves. So they are a bit of a time saver. I only like to use properly maintained, reliable ones that are, you can see they have lots of activity on GitHub and stuff like that. You don't want to use old ones that just random people create because you don't know if they're always going to work or like what they're doing in the background. So I never used to like using any modules, but now I kind of shifted. I do think it can save you quite a bit of time, and especially now a lot of these modules have become quite mature. They're quite reliable and they're used quite often. So we're going to define a module called VPC, and then we're going to type source equals Terraform-AWS modules/VPC/AWS. Now this is a hosted module. If you search on the Terraform modules website, you'll be able to find this one, and you can see all the versions listed there. So we're going to be using the latest current version, which is 4.0.1. And I put this tilde character because it means it upgrades or I believe it should upgrade the minor package when the new versions are available, just to make sure you have any security patches and stuff like that. Then we're going to do name equals, and the name, I'm going to use a variable here. So we'll jump back into variables.tf and we'll define a variable called prefix. And this is just going to be the prefix that we put on all of our resources. So prefix to be assigned to resources. And the default value for this prefix, we're going to call Django K8s. So just Django. This is short for Kubernetes here. So Django's Kubernetes. And this allows us to just prefix all of our resources in AWS. So if you're using AWS for multiple projects, you've got the same account for multiple projects, you can kind of identify what each one is for. So we'll do var.prefix here and -VPC. So that's the name of this VPC. CIDR, these are the kind of network IP address blocks that we want to assign. So I'm doing CIDR equals 10.0.0.0/16. Now this is a whole topic in itself. What this means, if you look up AWS CIDR blocks or CIDR blocks, it will explain what it means. It's kind of complicated to get your head around at first, but it makes sense. There's a lot of standard ones people use, like this is a common one that people would use for their address block for AWS, and this is the one that's in a lot of the tutorials and guides that you see online. It basically just determines how many network addresses you have and how many host addresses you have. And you want to make sure you've got enough of each one. This is a pretty safe bet in most cases. And then AZS, which is availability zones. And what we're actually going to do here is we're going to slice the first 3 availability zones that are available on our platform. And availability zones, just as the name suggests, they make sure that your service is available in different zones. So if one zone goes down, let's say London has a major power cut and half of it all goes down, then presumably they have another zone that you can fall back to that is always online. So this kind of helps with a single point of failure. So we'll do slice, which is a function that comes with Terraform. We'll do data.aws availability zones.available and then .name. Names. And this is that data thing that we added here. So availability zones available. This will just return a list of all the available zones, and we'll start from 0 and we'll take the first 3. So this is the syntax for the slice function here. Okay, now we can define our subnets. So we're going to split it up into private subnets, public subnets, and database subnets. We'll do private subnets equals 10.0.1.0/24, and then we'll do 10.0.2.0/24, 10.0.3 10.0/24. And then we're going to copy the same block and I'm going to paste it 3 times just for the sake of speed. I'm going to change the second one to public subnets. And this is going to be 10.0.10, 10.0.11, and 10.0.12. Oops. And then this one will be database subnets, and that will be 10.0.20, 10.0.21, and 10.0.22. Okay, we'll save that and it should format all nicely. What this does is it defines 3 different subnets for our VPC. The first one is the private, so that's internal only. It's not accessible from the internet. And it means that all of our nodes that are on the private subnet will be at 10.0.1 and then whatever the host name is. Or this will be unique per host. So if it's on 10.0.1, then you know it's in the private subnet. Likewise, if it's 10.0.10, then it's in the public subnet, which, as you might expect, means it has public access to the internet. And then you have the database subnets, which is specifically for accessing RDS database. So we have another subnet for that. So what this does, it just allows us to have different subnets and separate network connectivity on our VPC to private stuff that's internal only, public stuff which needs to either access the internet or be accessed by the internet, and database subnets which need to access our database. The reason I spaced them out like 10, like 1, 10, and 20 here is because if you want to add more at a later date, then you could go 4, 5, 6, 7 all the way up to 10 before you clash with this one. And likewise, here you could go 12, 13, 14, 15 all the way up to 20, and that usually gives you a bit of space to grow and keep the subnets organized. Okay, so next we're going to do enable NAT gateway. And this is the network address translation gateway, I think it's called, and it allows us to connect out to the internet. And then single NAT gateway equals true. And this is, I believe this is just for a cost saving thing. So ideally you would have a NAT gateway for each different zone, but we just want a single one for the whole VPC, which again is a single point of failure, but it's because I believe you get charged for the NAT gateway and you want to keep the cost low for the purpose of this demo. And then enable DNS host names equals true. This just allows us to have host names within our VPC. And then create database subnet group equals true. And we have to set this because we want to create a database subnet. The documentation for this can be found inside, if you load up the browser and you go to Terraform AWS module, then you can see the modules documentation here. It has various different modules available, and this is the VPC one. Again, it's all linked in the resources and the description of this video, or it might not be in the description, but it's definitely linked in the resources project that I shared earlier. So this tells you what all the inputs are and what they do essentially. So if there's something that I didn't clearly cover, then you can kind of, you can head here and you can read about it, and it should explain what these configuration values do. So a list of private subnets inside the VPC and so on. And if there's other things you want to do with your VPC, you can also find it in the module documentation as well. All right, so let's just continue with this. Now we are going to do public subnet tags equals, and we're going to do a tag called kubernetes.io/cluster var.prefix for dash cluster, which is the name of the cluster we're going to create in a bit. And we'll do equals shared. And what do we got here? So kubernetes.io cluster var prefix cluster shared, and then kubernetes.io/role/elb equals 1. I'll explain what these mean in a minute. So we'll do that for public subnet tags. We'll do that for private subnet tags as well. So, and these should be the same. So they should be exactly the same for both. And what this does is it lets you put tags on the subnets that allow Kubernetes to understand what to do with them. So the way Kubernetes kind of integrates with AWS, and you can configure different settings on the resources that allow Kubernetes to understand it. So we're basically saying that the public subnets are going to be shared amongst, I believe it means amongst all the nodes that are hosted on Kubernetes. We're going to create one ELB. So there should be ELB here. So Kubernetes IO role ELB. And this will create one load balancer that allows us to access services inside Kubernetes. So the load balancer gets automatically created when you create the service inside the Kubernetes configuration. Okay, so now that that's done, once you save, it should format it all nicely. We can open up our terminal here, and we can go into cd/infra. You got to make sure you're authenticated with AWS using AWS Vault, or you can use AWS SSO, I believe, which is the new single sign-on thing. But make sure you're authenticated, and then do Terraform init, and this will pull down the new modules that we've used. I got an error here, so I think I spelled default wrong. So we'll go ahead and correct that. Default, try that again. It's good because it validates every time you do this. So what this did is it pulled down the module that we have configured. So it caches it in the local system. It caches it in the Terraform directory here, which is why you need to have it all set up in your git ignore. Otherwise, it puts hundreds of things inside your git project, which you don't need. So we've initialized, and then we'll do Terraform apply. And what this will do is it will tell us what we are going to be doing when we apply this. So it's actually going to make requests to AWS and set up all this stuff. Now you can see it's got loads of things here. So if you scroll up, you see it's got route tables and VPCs and subnets and gateways, all this stuff. If you didn't use a module, then you would have to create all of these things and define them all manually yourself, which isn't the worst thing in the world, but it does save a lot of time to use these modules. So once you kind of read through and understand, or at least know what it's doing and know that it's not deleting anything from very important projects in your AWS account, you can type yes, and this will go ahead and create the VPC in AWS. So what I'll do is I'll actually log into AWS for you here. So we'll do, I might already be logged in actually, let's see. Actually, maybe not. So we'll, I am logged in here. So we'll go to my AWS account here, and we will take a look. We'll head over to the VPC, and you can take a look here, and you can see it's already created the VPC. So it's still creating some of the other stuff like the NAT gateway, but it's gone ahead and created the VPC here, and this will be used for the project. So we just need to wait for that to complete. While I'm waiting for that to complete, I'm going to go back to the project, do git add, git commit, and type the commit message, added VPC. I'm going to push this up to GitHub. And we're still creating the NAT gateway here. But basically, this will take a few minutes. The NAT gateway, or the VPC module, is generally pretty quick. I think it takes 1 to 2 minutes, which is a bit different from our EKS, or Elastic Kubernetes Service, which can take up to 15 minutes. RDS, which will also be creating that, used to take about 20 minutes, but I think they've recently upgraded it, because now I did it and it only takes about 5 minutes, which is really, really fast compared to how long I used to wait for that. But this is the thing with AWS. A lot of it's quite slow to create things. It takes a lot of time to create the resources that you need. But while that's going ahead, we'll just take a little review here, or I'll take a look at the comments. See, no questions or anything so far. That's great. We'll let this continue, and I will, there you go. So it's created 30 resources. These 30 resources would have all had to be defined, but we've managed to consolidate it all down into one module, basically, all thanks to the good folks that create this module and publish it for us. Okay, so the next thing we're going to do is create our RDS for our database. So we're going to build up the resources that we need. We're going to need the VPC, which we've done. We're going to need the RDS database. We'll need EKS and we'll need ECR and what's the last one? EFS. So we're going to work through all of these individually and deploy them all in their own time. So now onto the database. So I'm going to go to variables and we're going to define a variable called DB password. And we'll put description equals password for the RDS database instance. And we'll put default equals sample password 123. Now, in reality, what you would do here, if you were deploying this in real world, you would define this as a variable. You wouldn't set a default, but you would perhaps put the default in the password manager configuration that you're using. So if you're using GitHub Actions, you would configure the password as a secret in GitHub Actions, and you wouldn't hard code it in the project here like I've done. For demonstration purposes, this is why I'm hard coding it here. And also it's going to be on a private network anyway. So even though you all can see my password, you're not going to be able to access my database because it's not publicly accessible. It's all behind a private network. Anyway, that's what we will do. And maybe we'll cover something about how to do that in another live stream at some point in the future. If you want, then please just let us know in the comments if you would find that interesting. Or if you already know how to do it and you don't really care because you already know, you don't want us to waste time, then you could tell us that as well. Okay, so we've got our variables here for our password, and now we'll do rds.tf inside our infra directory, and we're going to create another module here. So this is another module that's provided by people that publish modules, and I can show you, well, let's look here actually. So if you go into the list of AWS modules, it should be here at the top somewhere, I expect. It's quite a popular one. So RDS, this is the module we're using here. So 5.9.0 latest, has all of the different inputs here, 89 inputs. We're going to be using a subset of them. So we'll start by defining source equals Terraform AWS modules /RDS /AWS. Version equal, get my typing right, version equals the little tilde character, I think it's called 5.9.0, and then identifier equals var.prefix -db. So that's the identifier for our database. Engine equals Postgres. I'll go through it all and then we'll talk about it as it's applying for time efficiency. We'll do engine equals Postgres. Engine version, we're going to use 14.7, which I think is the latest main supported one. Instance class equals db.t4g.micro, which should be available in the free tier if you're using the free tier. I've exceeded my free tier, so I don't get it for free anymore, but I think it's included in the free tier. And then it's family equals Postgres 14. Allocated storage, we'll give it 5. In reality, you give it more, but for demo purposes, we just need 5. Skip final, skip final snapshot equals true. I'll explain what that means in a bit. DB name equals Django project, and then username equals Django user. Create random password equals false. Password equals var.db_password. And then multi_az equals false. And then db_subnet_group_name equals module.vpc.database subnet group. We haven't created that yet. Oh no, we have. That is created. That's created as part of the VPC module. And then VPC security group IDs equals module.rds security group .security_group_ID. And this we're going to create in a second. So again, I'll talk through this in a moment after we've typed it all out and we're applying it just for the interest of time. Module RDS security group source equals Terraform AWS modules /security group /AWS. And then a version equals tilde greater than 4.17.2. And then name equals var.prefix -rds -sg. Description equals RDS security group. VPC ID equals module.vpc.vpcid. And then we will do ingress underscore CIDR underscore blocks equals from port equals 5432 to port equals 5432. Protocol equals TCP. And description equals PostgreSQL access from within VPC. And then CIDR blocks equals module.vpc.vpc CIDR block. Okay, next we have the DB password variable is already set. Okay, so now what we can do is we'll just go back to our terminal here and do Terraform init to pull down the latest modules that we've added. And then Terraform apply, which is going to apply the changes. I made a typo there, as you can see, skip final snap show, which should be snapshot. And then we can apply that again. Invalid value for input variables. So what have I done here? So let's take a look. It's in this block here. So we got ingress. It should be ingress with CIDR blocks. That's what I did wrong. Let's try that again. Okay, it looks a bit better now. It's past the validation. And this is going to go ahead and create a RDS instance for our database. We'll type yes. Okay. And now that's applying. That's going to take like 5 minutes. So I'll talk you through what I did here, and then I'll take a look at the questions. So we define a new module with the source Terraform AWS modules, RDS AWS, and we pin the version to 5.9.0. The identifier is just basically the name. So we put our prefix -db so we can see that. We can actually see that inside AWS. So we go to AWS and then RDS. You can see it should, if this page loads, it should have our RDS instance being created under DB instances, Django K8DB. And then we've got our engine, which is Postgres. That's the kind of the software on the database. And then engine version, which is 14.7. It's just the latest version that's supported. And then the instance class is the server that it runs on. So you can get various different ones of these in various different levels of power. So they cost more, the more powerful they are. This is the cheapest possible one, I believe, that you can get, which I think it is included in the free tier, but you might want to double check that. So if you're using the free tier, then you shouldn't be charged for it. And then we got the family, which is Postgres 14. Now, I don't know why these need to be kind of duplicated here, but they do. I tried it without family and it said it needed all of them basically. Allocated storage is 5, so it's 5 gigabytes that will be stored. And skip final snapshot true means when we destroy this database, it won't make a final snapshot. Now, this is just for development purposes. In a real situation, you do probably want the snapshot because you want the snapshot contains the data in the database that was destroyed. So I wanted it to be smooth for the Terraform for creating and destroying because I'm just creating it here for learning purposes. So I put skip final snapshot true. If you're doing it in a real world situation, you might want to think about setting that to false. Got the database name, which is the name of the database going to be created inside RDS, and the username of the user that's going to be able to access. Create random password is false because we don't want it to create a random password. We want it to we want to create our own password, and the password we create is what we define in var.db password. Multi-AZ false. Again, this is cost saving. If you want, if you turn this on, then it costs more to run your database. Putting it as false just means it's not available in multi availability zones. DB subnet group name. So this is the subnet group that is defined inside our VPC module here. So the database subnets, it creates a group in the background and stuff, and it allows us to access it through the subnet group here. Just check I did that right. Yeah, it looks like that was right. Okay, and then VPC security group IDs. This is the security group that we're defining here, which provisions what can be accessed. So we want to say, we basically say here, we want to be able to access our database on port 5432, which is what RDS or what Postgres runs on, using TCP and from our VPC. So the CIDR blocks in our VPC, we can access the RDS instance from anywhere in the VPC. And that's because our hosts that run in our VPC could be created on any of the subnets. Okay, so we'll see how that's going. It's still creating the instance. So let me take a look. I think we have a couple of questions here. So Ganesh, let's see. So can you share any quick guides on having Kubernetes connection to RDS in AWS? Well, we are doing that in this guide here. So I don't know if it's going to be quick. I'm hoping we can get it all done in the next hour and 10 because we try and keep these to 2 hours. But yes, we will be connecting to RDS from our Kubernetes deployment. So hopefully that's covered at the end. If not, then please let us know. Why do we separate module for ADS? I assume it means RDS security group. So why do we separate module for RDS security group? Why can't DB module have this security group included? I think this module actually creates the security group, and then we assign it to our module here. Perhaps I misunderstood some of the configuration. Maybe this module does support that, but this is the way that I did it here. So if it does support that, then apologies. If you could create this security group from within this module and it supports that, then that's great. That would also save you some time and save you from adding this additional module here. It is useful to be able to add your own module and just for the sake of learning how to do it. But yeah, thanks for the questions, Ganesh. I hope I pronounced your name right, and I hope that that answered the questions for you. If not, then just let us know. All right, so let's continue. Well, we can't really continue till this is done, but you can see it's done here. So it took about 4 minutes here, and it added 4 resources. So you go in here and you can see our database is up and running. Obviously, make sure you're in the right region if you're looking at this yourself, because if you chose a different region, then your resource is going to be created in that region. Okay, so let's move on to the next step. So the next thing we're going to do is create EKS, and this is what takes a lot of time. So it's going to take some time for us to write it out, and then it's also going to take some time for it to apply. So what we'll do is we'll write it all out, we'll apply, and then while we're waiting for it to apply, we can go through, answer questions, or have a quick break, whatever people need. Okay, so inside this, let me just commit this up. So git add, git commit, added RDS. Push this up to GitHub in case people are following along that way. Okay, so I'll close these tabs here, and we're going to create a new file inside infra. 2 new files actually. So we're going to create one called EKS.tf and one called outputs.tf. We'll talk through what these do in a bit. We'll start with EKS. Okay, so we're going to create a new module for EKS. We're going to use the EKS module that is provided in the Terraform modules here. So EKS, this is the module that we're going to be using. And again, it has examples and it has all this, all the configuration, everything that you can do. And actually, Terraform have a guide. So if you go onto Terraform EKS, there is a guide here that's linked. So provision an EKS cluster. And that actually walks you through something quite similar to what we base this on. So I kind of went through this, but then obviously I built on top of it and adjusted it for what we need to do. But this explains things as well. So if you wanted to do that in, if you wanted more understanding of this specific module, then this would be a useful thing to take a look at later. It should be in the resources. Okay, so we're going to define locals. cluster name equals var.prefix colon or hyphen cluster. And this is just like a little local variable that we can reuse. And then module EKS, and we'll do source equals Terraform AWS modules /EKS/AWS. And then version equals, again with the little tilde symbol, 19.14. And then cluster name equals local.clustername. And cluster version equals 1.26. And VPC underscore ID equals module.vpc.vpc ID. Subnet underscore IDs equals module.vpc.private subnets. And then cluster underscore endpoint public access equals true. And then cluster underscore endpoint underscore public underscore access underscore CIDR equals. Now you can do this as either 0.0.0.0/0, and this makes it publicly accessible to everyone. That is not what I recommend. I recommend you lock it down to your IP address. So if you go into your favorite search engine, I like to use DuckDuckGo, type what is my IP, and it will tell you this is your IP address here. So we're going to take our IP address, and I'm going to paste my IP address here, and I'm going to do /32, which is the standard for public ISP IP addresses. This essentially locks down, so only I can access it from this IP. So if you're following it, you can't take my URL and access it from your IP. You have to be on my network. So it's a security thing, and it's recommended not because it's the only type of authentication, but it just makes it a lot more secure than having it publicly accessible, in case there's any vulnerabilities that allow people to circumvent the login or something like that. But we'll talk through that in a bit more detail in a moment. So we'll do EKS underscore managed underscore node underscore group underscore defaults equals AMI underscore type equals AL2 underscore x86 underscore 64. And then EKS underscore managed underscore node underscore groups equals node underscore group equals name equals AL2. No, not AL2, sorry, that was what we typed above. So the name of this node group here should be K8s-NG-1. And then instance underscore types equals T3.small. And then min underscore size equals 1. Max underscore size equals 3. And then desired underscore size equals 1. And then labels equals environment equals dev. And then under this block here, so 1, 2, 3, 4 close brackets here should exist. We're going to add another module called module VPC underscore CNI underscore IRSA. And then source equals Terraform hyphen AWS hyphen modules /IAM /AWS, then double / modules /IAM hyphen role hyphen for hyphen service hyphen accounts hyphen EKS. Quite a long one there. And then version equals the tilde greater than 5.19. Role underscore name underscore prefix equals var.prefix hyphen VPC hyphen CNI hyphen IRSA. And then attach underscore VPC underscore CNI underscore policy equals true. And VPC underscore CNI underscore enable underscore IPv4 equals true. OIDC underscore providers equals main equals provider_arn equals module.eks.oidc oidc_provider_arn, and then namespace_service_accounts equals kube_system:/AWS-node. There's a lot there. There's quite a lot there. Okay, so save the file, and hopefully you managed to type that out with me. If not, you can just simply go over to the project and you can copy it if you got kind of lost there, because there's quite a lot there. So don't blame you if you did get lost. But if you go to github.com/London app developer, you should see our project there. We should be under AWS Django EKS tutorial. And again, this is the complete code. So this is everything all finished. It's basic. So basically you could use this to copy and paste. That's EFS, not EKS. But the reason why I type that really quick is just because this takes like 15 minutes to apply, and I just don't want us to overrun. So what we'll do is we'll just finish this. We just need to open up outputs.tf and type output cluster_name description equals name of EKS cluster in AWS, value equals module.eks_EKS.cluster_name, and then a second one, output region, and this is called description equals AWS region, and value equals var.region. All right, let's just get this applying, and then I promise you I'll explain what all of that stuff does. So I'm going to move into my infra again and do Terraform init, and we'll see. Maybe I find it hard to believe I didn't make any typos in all of that. So let's see, what's this here? Does not exist or cannot be read. So there's a problem with our service account modules. I must have put a typo somewhere in there. So let's take a look. What did I type wrong? So Terraform AWS modules /IAM/AWS, then // modules here. So that should be modules plural. Modules, and then IAM role for service accounts EKS. Let's try that again. Okay, let's pull that down. There is also a Terraform validate command that you can run. So Terraform validate, this will validate it's all valid, and you can see it's not here. So cluster endpoint public access CIDR. So what did I do here? So cluster endpoint public access CIDRs should be CIDRs plural. So we save that, fix that, save that, validate that, should be good. Okay, success. That's good. Now we'll do Terraform apply. This will tell us what it's going to do. It's probably going to create hundreds of resources. Okay, 33. So again, these 33 resources, you would have to create them manually if you didn't use this module. But we use the module, so it saves us some time. So you can look through this, just make sure it's doing what you kind of expect, and then you can hit yes, and yes, we'll go ahead and apply. So this is going to take some time. So it'll give me some time to talk through this stuff. So locals is a variable that we define that we can reuse wherever we need to get the cluster name. So we kind of define this once, and then we can use it as a kind of template. And then we have module EKS, where we define our module, and we're using the source and the version that is the latest version available of that module. Then we're setting the name of the cluster here, and then the version. The version of the cluster is 1.26. That's the latest version of the Kubernetes that is available at the time, or at least the latest version that's supported by EKS. Then you have the VPC, which links to the ID of the VPC we created inside vpc.tf. And then we have the subnets of that VPC. So we're assigning the private subnets because we only need access via our private subnets from Kubernetes. And then we're doing cluster endpoint public access. And this says we want to make our endpoint to our Kubernetes cluster publicly accessible. But what we do here is we set our IP address and we lock it down. So even though it's publicly accessible, only our IP address will be able to access. Now, obviously don't use my IP address because you're going to want to connect yourself. So this would be your public network IP address of your local network. If you don't know what it is or you don't want to and you're happy to make it public, then you can just put 0.0.0.0/0. That makes it totally public to the internet. There is authentication, but for security purposes, generally that's not recommended. It's best practice to lock it down as much as possible. Then we have our managed node groups. So with EKS, there's various different ways that you can host nodes. So one way is EKS managed nodes. So what this means is EKS, the Elastic Kubernetes Service, is going to create the servers for us. So it creates the servers as needed for our cluster. So these servers get created and they get added and taken away as needed. We don't need to manage the servers ourselves. They're all managed by the service. So what we're saying here is the managed node group defaults. So for every managed node group we have, the default is going to be AMI type AL2 x86-64, which is Amazon Linux 2 on the Intel x86-64 architecture, instead of their newer kind of ARM architecture stuff. Now this means that you can run kind of standard Docker images that you compile if you're using Intel processor. Otherwise, you have to compile them specifically for the architecture that you're deploying to, which not everything supports yet, but basically everything is moving towards the ARM processors anyway. So eventually that support will be full and you can kind of switch this out for the newer Amazon kind of ARM-based processor servers. Okay, and then we have EKS managed node groups. So this is the, you can add multiple of these node groups. We're just adding one. And this defines the group of nodes that we want EKS to manage for us. So we want to give it the name K8NG1, which stands for Node Group 1. And we're setting the instances here. So it creates instances for us, and these instances will be charged onto our account. So whatever you set the instance type here to, it will create instances and you'll have to pay for those instances. Now I'm using one of the smaller options that you can get. You can get bigger, more powerful node instance types, which obviously cost more. You need to do a calculation on the AWS cost calculator to see what those costs would be. And now we're saying the minimum, maximum, and the desired size. So we're saying at minimum, we want one node running all the time. Maximum, we allow it to go to 3 nodes. And ideal in a given situation, we just have one node. You can obviously tweak these based on your deployment, but it basically affects the cost. So if you have minimum size 5, it's going to have 5 nodes running all the time, which means you're going to be paying for 5 nodes running 24/7. So it's better to have the lowest minimum that you need, and the maximum just means if you had a lot of traffic to Kubernetes, a lot of pods created and stuff like that, there is an upper limit. So you're not going to get charged an infinite amount for resources. It will only ever scale to 3 different resources. You can obviously increase this based on what you need to scale to. And then desired, I think this is just kind of the desired default state. I'm not exactly sure what this means. I should look up what desired means. But I've seen examples where min is 1, desired is 2, and max is 3. Obviously, I do know that your desired needs to be either equal to or more than the minimum size, but it can't be more than the maximum size. Labels here, this is just an optional label. You can give any labels that you want. The reason I did this is because there seems to be a bug with the Terraform module that every time I would apply, it would update the labels if there wasn't any labels set. But this gets away with that or fixes that by explicitly setting labels here. It's also useful to know how to do. Okay, let's just check this is still going. Yeah, okay, we're still going. Then we have the module here. So the module is, the module for VPC CNI RISA. So IRSA is the IAM role for service accounts. So the way that Kubernetes works is Kubernetes is its own technology. It's its own kind of server and manages the servers in a certain way. And it has its own accounts, its own users, its own all kinds of syntax inside a Kubernetes cluster. Now, because it's running on AWS, and if you want to communicate with AWS services, there needs to be some kind of connection there. So Kubernetes needs to be able to access AWS, and it needs to be able to have permissions to do that so it can kind of integrate. So the way that you do that is you use service accounts. So you can give a service account to something in Kubernetes, and you could tell AWS to allow that service account to do certain things. So what we're doing here is we're allowing the service account to attach the VPC CNI policy. So VPC CNI policy is what allows it to mount basically network adapters to our VPC, so it can access and integrate with the VPC resource in AWS. And that's basically what this does. So we're setting up a role here. This will create a role called var prefix VPC CNI IRSA. And then we're using this OIDC provider. And OIDC provider is kind of the link between Amazon and the service account inside Kubernetes. So there's a Kubernetes service account called AWS Node, which is set up by EKS. And that is the service account that the nodes run on. So this block here allows our nodes to work with our VPC. And that's my understanding of how this works. Okay, so the other thing that we created was outputs. Now, outputs, we have a cluster name and a region. And this is because we're going to need this information once our Terraform has been applied in order to authenticate our EKS service with the Kubernetes command line. So I'll show you how to do that in a moment. All right, so we're about 10 minutes in. We've got about 5 minutes. I'll take a look at the questions again. Okay, sorry, Ganesh. Ganesh said he meant Kerberos, and not Kubernetes. Now, I'll just be totally honest. I don't really know much about Kerberos. I've heard of it before, but I certainly don't know enough to answer your question, unfortunately. So sorry, you might want to ask that one to the search engine or ChatGPT or something. Yeah, I'm not sure how you would do that. If we get enough interest in that topic, then perhaps we can make some content on it. I can learn how to do it, and then we can make some content on it in the future. But yeah, sorry, not much use there. Okay, so it doesn't look like we have any other questions. Apologies for losing the audio. Let me just check the battery levels. We seem to be good. We got 2 bars on the receiver and fresh batteries in the transmitter. So hopefully we don't lose again before the end of the stream. So we are still applying this. So it's going through, it's creating our node group. So what Kubernetes or Elastic Kubernetes Service does is if you go into the console here, it's actually created our cluster already here. So you can see it's got the cluster, status active, Kubernetes version 1.26. And then it's got all the information here. So I think it's still loading, which is why we got an error here. It's still creating. But basically, you can view all of your resources here. So let's see if it has any nodes so far. So compute, this is our node group. And you can see it's creating our node group. So the node group is what basically manages the servers that run in EC2. And I think if you go to EC2, you can actually see them running. Okay, they're not running yet. But essentially there are 3 ways that you can use EKS. So one way is you do what we're doing here, which is you allow it to create its own managed group. So EKS manages the node groups for us. You tell it what you want and it creates it and manages it for you. The other option is you create the node group and you link it up. Now, this is more complicated because you have to create the servers, you have to create the groups, you have to do all of this stuff, and then you have to connect it into your Kubernetes cluster, but that can be done. The third option is you use Fargate, which is the serverless option. So you tell it to run our pods in Fargate instead of running them on actual virtual machines. And that's a different approach, and all of those examples are available in the documentation for this EKS module. I went for this approach because it seemed like the simplest. It kind of demonstrates how it works, and yeah, this is the one I chose for this. Okay, so let's see where we are. So we're still creating. Maybe what I'll do is just in case anyone's waiting for me to push this up, I'll just commit this. So git commit added EKS. And then we'll push that up. And I think what we can do while we're waiting for that is we can kind of move on to the next thing while it's applying, because I don't want to take too much time here. Oh, it's done. Okay, perfect. Okay, so this is all created. If we go into here, you can see our instance running. So it's running one instance for us. And you should see our EKS cluster should be healthy, active, all good. Okay, this is running. The next thing we're going to do is create ECR. A lot of acronyms in AWS. The name itself is an acronym, which probably tells you a lot. So what we'll do is we will create a new file here called ECR.tf, and this is Elastic Container Registry, and it allows us to have a private container repository that we can use. So we'll go ahead and someone asked about, let me just see what this question is. So Carlos, thanks for the question. Greetings from Colombia, South America. Thanks for the knowledge. Thank you. Appreciate you being here. So is T3 small to run a lab or for Kubernetes? Yeah, so this is just for testing, like kind of lab type demo. And it's one of the cheaper options. So because I don't want you getting charged too much, I use the lowest option, and that's perfect for this tutorial. You can obviously increase that to more powerful instances, but it does have a cost associated with it. So you just need to be mindful of how much it costs. Okay, so let's go ahead and let's create our ECR, which is going to be used to store our Docker images that are going to be deployed to Kubernetes. So we'll do resource, AWS ECR repository, app, and then name equals var.prefix -app, and then image underscore tag mutability equals mutable. As I said before, I'll talk through this at the end. Force delete equals true. Talk through this at the end once we are deploying. Image scanning configuration. Scan on push equals true. And then a resource, AWS ECR repository proxy. So what I'll do is I'll just copy this, save time. Copy this. So it's exactly the same as app, except it's going to be proxy. And this name here is going to be proxy. Everything else is the same. And then we're going to do resource AWS IAM policy. Allow ECR app. And name equals local.cluster underscore name -read ECR app. And then policy equals JSON encode. And then we're going to encode some JSON here. So version equals 2020 or 2012-10-17. And then statement equals, and then square brackets here, statement equals effect equals allow, action equals ECR batch check layer availability, and then ECR :batch get image, and then ECR :get download URL for layer, and then ECR :get authorization token. And then under that action block here, we'll do resource equals AWS underscore ECR underscore repository dot app dot ARN. Okay, and this, we can save this and we can copy this and duplicate it, except we're going to change the name here, allow ECR proxy, and then read ECR or EKS, I missed the EKS, or we don't need the EKS actually, read ECR proxy. And then everything the same here, and then just change this bit here, the resource to proxy. So that's the ECR created. Now we just need to do one more or two more things. So go to EKS.tf, and we need to assign the policies here. So underneath, let's say between the EKS managed node group defaults and the cluster endpoint public access CIDRs, do IAM_role additional policies equals, and then we'll do allow ECR app equals AWS IAM policy allow ECR app dot ARN, and then allow ECR proxy equals AWS IAM policy dot allow ECR proxy dot ARN. And then we'll do outputs. Look at the outputs here. We're going to add a couple more outputs. So output ECR app URL description equals ECR repo name for app, and then a value equals AWS ECR repository.app.repository URL. Copy this. This is going to be app and proxy. So ECR for proxy. Dot proxy. Okay, so that's done. Now let's go ahead and see if this is valid. So we just need to do Terraform init. Okay. Terraform apply. Yes. Okay, that was quick. I did it really quick, so I don't really even have time to explain why it's doing that, but I'll explain anyway. So the repositories are in AWS. If you go to ECR, Elastic Container Registry, sorry, it's Elastic Container Registry, not repository. So Elastic Container Registry, and this is where you can store Docker images. It's like a private Docker hub. So we're defining one here. We're defining one for our app and one for our proxy. So if you followed the previous tutorials, you'll know that our Django app is kind of split into an app and a proxy container. The proxy forwards things to the app and also handles static files and stuff. So we got the name, and then mutable means that you can update the tags. So you can have a tag called latest, and you can update that latest tag. If it's immutable, that means that you have to have a unique tag every time you push. Now, and that means you can't have something like a latest tag, because it would have to be latest 1, latest 2, latest 3, whatever. So I prefer mutable just so we can have a latest tag. This really depends on your workflow. Force delete is true, which means if we destroy this Terraform, we want to clear the resources, it will force delete even if there is data inside the repository. And then image scanning on configuration is just security scanning of the image. And this is, we've got one resource for app and one resource for proxy. Then we have the policy here, the IAM policy, which allows us to assign a policy to the nodes that are using it, so they can actually make requests and access our repositories that we've created. So we're doing one for the app and one for the proxy. And these are the permissions that you need. If you search ECR access policy or something like that, then AWS have a document where they explain what the requirements are. But this is the requirement for something that needs to pull images. So it doesn't need to push, but it just needs to be able to access. So it needs to be able to check layer availability, get batch, get image, and then get download URL for layer, and then get the authorization token and so on. So we're doing a policy for both of our images or our image repositories, and we are then inside EKS assigning it to the policy here. So the nodes can access ECR. So that's how our Kubernetes cluster is going to be able to get images to run. It can get them from the public internet if they're on Docker Hub publicly, but if you want a private image, you need to do it this way. Okay, great. So what's next? Let's commit this up. So added EKS and ECR. Oops. Push. Oops. Commit. Okay, push that up. And next, what we're going to do, we're getting there. We'll be done. We're on step 7 of 14. We're halfway. So I don't know if we're going to get everything done in the 2 hours. We might overrun a bit, so apologies for that. But if you need to log off, then you can always come back later on and review it. We'll put it on the channel, of course, available after the stream. Okay, so the next thing we're going to do is we're going to set up our dashboard and actually connect to our Kubernetes service. So we'll do that by running a command. So we need to be inside our infra directory. We'll type AWS EKS -- region, and then this is the region. So I'm on EU-West-2. If your region is different, then you would obviously put a different region in there. We'll do update kubeconfig, and then -- name, and then the cluster name. So you can copy it from here actually. It's probably easier for everyone. Copy the cluster name, and then hit enter. And you need to make sure you're authenticated with AWS CLI. And what this will do is it will set up our local Kubernetes configuration so that it can authenticate with our new cluster. So you can test if it worked by typing kubectl get, not get pods, you want to get nodes. So if you get nodes, you should see one node, and this is the node that we have running in our service. If this has one node, then you know you've done it correctly. Okay, and the next thing we're going to do is set up, now that we've authenticated, we have command line access, we're going to set up the dashboard, because the dashboard is really useful to be able to see what's happening in Kubernetes, but it doesn't come installed by default because not everyone needs it. So you have to install it manually. There's a few ways of doing it. If you go to the resources, the description, or if you just search for Kubernetes install dashboard, there's a good documentation guide here. So deploy and access the Kubernetes dashboard. So it has this here. So they have a recommended configuration, which is hosted for you for your convenience, that you can just simply paste and it will configure the dashboard for you, which saves quite a lot of time. So that's what we're going to do. We're going to use that. So we're going to start by pasting that. Hit enter, and it should create a bunch of resources. Okay, so the resources are created, but it doesn't actually create everything because it doesn't create a service account for you to use. And I think that's because there's different recommended approaches for managing service accounts. You typically don't want to use a service account to connect this way. You would typically create an individual account per user who needs access. Now, for the interest of time, we're just going to create a shared service account that we're going to use to connect. So in the deploy directory, this is our Kubernetes config. We're going to create a new file called dashboard-sa.yaml. We'll do API version v1. Kind is service account, and metadata is name admin -user, and namespace is Kubernetes dashboard. Okay, save the file, and then we are going to apply this by doing kubectl apply -f for a file. We want to apply a file, and the file location, because I'm in infra right now, I need to go back directory and then deploy and then dashboard-sa.yaml. This creates a service account that we can use to connect. And then we need to create what's called a cluster role binding. So it gives access to our service account to allow us to be able to log into the dashboard. So we'll type kubectl create cluster role binding service accounts -cluster -admin, and then -- maybe I'll just make sure this isn't, my head's not in the way or something. So just move this up here. So -- cluster role equals cluster -admin, and then -- group equals system : service accounts. Hopefully I typed that right. I did put this in the documentation as well, so I put a mistake here. So cluster role is wrong. Cluster role, like that. Okay, so it's created that. So hopefully that's all we need. Next, we can do kubectl. So this basically gives access to the user that we created to be able to authenticate and connect to the dashboard. So we'll type kubectl create token admin-user, which is the user we created in our config, admin user here. So we're going to create a token for that user. So create token admin user. I'm going to do duration 4 hours. So it means this token's valid for 4 hours. And then -n, which is namespace, Kubernetes -dashboard. That's the namespace we're creating the token for. Hit enter, and it creates this little random token here. So this is what we need. It's essentially our password. So keep it secure. Because I've locked it down to my IP address, you shouldn't be able to access. And also you need to create a proxy on my machine anyway. So it doesn't matter that you can see this, but ideally you don't want to be sharing this out to people. Now we're going to type kubectl proxy. And what this will do is it will create a proxy that allows us to connect from our local machine into our configured cluster. So before I head over to the proxy site, or we'll open up the docs here. So it's actually a long URL. You need the specific URL to the namespace here. So this is the URL that you can access on. So if you on this documentation page, you can click on this. It's localhost 8001 API v1 namespace, Kubernetes dashboard services, and then the HTTPS Kubernetes dashboard proxy. Anyway, this is the dashboard here. So it's connected into our local machine and it's forwarding the connection to our EKS instance. So now we can take our token and we can copy this token and we can paste this token here and click sign in. And now we are in our Kubernetes dashboard. So if you change the namespace here, just do all namespaces and you go to nodes, this is our node running in AWS, and as it creates more nodes, they'll appear here, and as it deletes nodes, they will be removed from here. So this is a basic Kubernetes working using EKS. Next, what we need to do is we're going to set up EFS, Elastic File System, and then we're going to deploy our app. So someone asked a question. So from Anis, thank you for the question. So which is better, a Postgres install on Kube or class install? I'm not sure I fully understand what you mean by that, but I think what you mean is it better to install Postgres in Kubernetes and run it in Kubernetes, or use a service like RDS or something like that? So my answer to that would be I would use RDS, and that's why I used it for this, because I tried to get Postgres running as a pod inside Kubernetes, like I did in the previous live stream where we had Minikube. I tried to get that working. I tried for days, but there's issues with the permissions and the file system, and it's very hard to have a persistent file system that works well with Postgres running in Kubernetes. And at least that was my experience. Now, maybe there's something I missed. Maybe there is an easy way to do it, but I couldn't find any nice, easy to use guides that shows you how to set up Postgres and use a persistent file system that allows read-write many to many different nodes and works with Postgres. So if anyone knows how to do that, I'd appreciate a link or something, because that would be really useful to know, as it means you don't need to have an RDS resource. Okay, so back to the steps. Next, we are going to create EFS, the file system. So we need to go back to our code, and let me just commit this and push it up. So do new tab, git add, git commit, added dashboard, SA, push origin. Okay, so next we're going to create, as I've said, I think about 3 times, create EFS. So we'll open up our infra, new file called EFS.tf. And then in here, we're going to use resource AWS EFS file system data. Let's see, I think we have a follow-up to the question here. Yeah, so sorry, just to follow up on you Anis, hopefully I said your name right, Anis. Yeah, so Kubernetes, you could run it in Kubernetes, but it would need to be highly available, and you would need to do kind of quite a lot of configuration. If you use RDS, then that takes away some of the overhead, because that does it all for you. You can put it in multi-AZs quite easily, and it will be managed and upgraded and everything for you, so you don't have to manage that yourself. Obviously the downside of doing RDS is it costs more money, so it'd be cheaper if you could run it on Kubernetes, but like I said, it's not cheaper if it takes me weeks to figure out how to do it, because obviously time is valuable. So yeah, if someone did know how to easily get that running on Kubernetes, then that would be great to know how to do that. Okay, back to this. Let's create the EFS. So creating the file system. So we'll do creation token equals module.eks.cluster_name -data, and then tags equals name equals module.eks.cluster_name -data. That's our basic Elastic file system resource. And then resource AWS EFS mount target data count equals length module.vpc.private_subnets, and then file system ID equals AWS EFS file system.data.id, and then subnet ID equals module.vpc.private_subnets count.index, and then security groups equals AWS security group.allow EFS.id. And then we're going to create that security group. So resource AWS security group allow EFS name equals local.cluster name allow EFS SG description equals allow EFS access for EKS cluster. VPC_ID equals module.vpc.vpcid, and then ingress from port 2049 to port equals 2049, protocol equals TCP, and CIDR blocks equals module.vpc.private_subnets CIDR blocks, and then tags equals name equals allow EFS access for local.cluster name. Okay, now we're going to do module EFS CSI IRSA role source equals you can copy the same source as the EKS role here. So this one here, it should be the same. So we'll copy that, and then we'll do version. Again, it's the same version, 5.19.0, and then role name prefix equals var.prefix -EFS -CSI, and then attach EFS CSI policy equals true, and then OIDC providers equals 1 equals provider_ARN equals module.eks.oidc provider ARN, and namespace service accounts equals kube-system :EFS CSI controller-SA. Okay, save that, and then we just need to add some outputs, and then I'll talk through what that does. So output EFS CSI SA role value equals module.efs_CSI IRSA role.iam role ARN, and then output EFS ID is value equals AWS EFS file system.data.id. And then what we got here, output DB instance address. So this one we probably should have added with the database, but we can add it now. Description equals the address of the RDS instance. Value equals module.db.db underscore instance underscore address. Okay, and then save the file. So go ahead and make sure that's all saved. We'll apply that by doing, I just need to do AWS Vault again. And then we'll do Terraform init to pull down the latest modules, and then Terraform apply. We'll see if there's any errors or typos in this. Syntax. Yes, okay. Looks okay. All right, so what we're doing here is we're creating an EFS file system. It stands for Elastic File System. The creation token is essentially, I believe, like the name of the file system. I don't know why it's called creation token, but we're calling it cluster name -data. And then tags name, you can give it a name here as well. And then EFS mount target. So the way EFS works is you create a file system and then you need to set mount targets to be able to mount onto the file system in order to use the files or use the file system. So put data on the file system. So we're using the count here to use kind of the interpolation that comes with Terraform. So we can basically essentially run this for the number of counts that we set here. So we're using the count of module.vpc.private subnets. So for every private subnet, we're going to create one of these resources. And to that resource, we're going to assign the file system ID, which is the ID of the file system we created, and the subnet ID, which is the subnet that we are iterating through. So it's kind of like how you do a loop in Terraform. And then we're assigning the security groups here to provision access. So the security group here allows us to access ingress, so inbound access on port 2049, which is the port required to connect to EFS. And we're allowing that on the CIDR blocks for the private subnet. So anything in the private subnet of our VPC can mount and use data in our EFS file system. And then we're setting this role here. So this is the service account role that will allow us to connect. We're going to install an EFS kind of driver onto Kubernetes, and that needs to be able to connect to EFS and mount file systems. So in order to give it permission to do that, we need to attach this EFS CSI policy, which allows for that to happen. So that's what this is for. It's a service account, gives the service account access to EFS. Okay, so let's just check questions real quick. Thank you, Anis. Really appreciate that. Yeah, hopefully. So that's what you meant. If you run it on Kubernetes, I think you need HA. Yeah, I would say if you're doing it in production, you would need high availability enabled because you don't want your single point of failure database to go down. Yeah, hopefully that answers that question. Okay, so let's see if this has applied. Yes, it's applied and it's put the outputs here. So the reason why we added these outputs is because we're going to need them in a moment. Okay, so we've created the resources. Next, what we need to do is we're going to use Helm. So someone suggested Helm. My good friend Greg also suggested using it. It's kind of like a package manager or configuration manager that allows you to apply some predefined configurations to your Kubernetes cluster. So if you look at what you need in order to mount onto the EFS file system is you need something called the driver, the CSI, EFS CSI driver. So if you search for AWS EFS CSI Driver, the documentation actually explains how to install it, and it suggests doing it through Helm. So that's what we're going to do. We're going to use Helm. Hopefully you have it all installed. If you go to this page, which should be in the resources, the first thing you need to do is add the repo here, because that's how it kind of works. Is it's like repositories that you assign to your local Helm setup. Mine already exists as I did this earlier, but if yours doesn't exist, then it should add that. Now what we need is the role ARN. So if you type, we need to use the Helm command to install it, but we need to tell it what role to give to the service account. So this is my role ARN here. So you can copy this, you output this, so do Terraform output raw EFS, or it's output here as well actually. So you basically want to copy that, and then this command here, so we actually change it a bit for the course. So if you go to the tutorial here, it might be easier just to copy it from here because it's quite a tedious command. But essentially it's this Helm upgrade, and then the I means install, so it means install it or upgrade it. So we paste that. So we'll paste it in and we'll change it. So this image repository here is unique per region. So if you're using EU West 2, this is the one you need. If you're not using EU West 2, then on the documentation page here, it has a container image address link, and it tells you which one for your region. So you find the one for your region. Using EU West 2, this is the one we're using, and you want to use the one for the region you've deployed your cluster to. So we have the namespace kube system, which is the main namespace for the Kubernetes system. And then the image, this needs to be correct per region. And then we're actually going to create the service account with this command. So we'll do service account create. We'll call the service account EFS CSI controller SA, which needs to match the service account here. So it should match this account. And let me just check that I typed that all correctly, because if it doesn't match, then you run into issues. Okay, that seems like it matches. And now you want to put the role ARN here. So that's this one that will be generated based on your Terraform. It'll be different for everyone. So you're going to paste that in and then hit enter. And hopefully it goes ahead and installs this. So the way that you know it's installed, you can actually do this if you want. Or you can go into the Kubernetes dashboard that we should still have open here. See if we're still, no, we need to log in again. So if you get this, it times out. You need to basically go and get the token that you generated earlier, or generate a new token and paste it in. So if you go on to namespaces, kube system, and then pods, the way that the driver works is it runs a pod that manages the connectivity. Now, because I think this one always seems to be pending, and I believe it is because we only have one node and it's trying to run two pods. So it can only run one node per pod, I believe. And that's why this is pending. I think if you spun up extra nodes, it would this would work, but it doesn't stop the functionality from working in my experience. So this is the driver that's running. If you need to see the logs for it, you can click it, and you can click on the logs here, and it should tell you if there's any permission errors or anything like that. This looks okay to me. So the next thing we need to do is we need to modify. This is kind of almost the last step. We're almost there. We will probably be delayed a bit, but we might just make it. So I'll commit this. Added EFS. Okay, so next we need to update our configuration to essentially be able to configure our images. Actually, first we need to build and push our images, which is a step that we were supposed to do earlier, but I kind of skipped. So we need to authenticate with ECR. So if you search for authenticate with ECR private, it gives you the command in the AWS CLI to authenticate. So it's basically this command here. You need to know your region, and you need to know your account ID and the region, and you can run that command. So you can copy this, and we'll paste it, and I'll fill out the details. So we need the region I'm using is EU West 2, and the account ID, this is unique for everyone's account. So you're going to have your own account ID, obviously. So I'm using my account ID here, and I also need to put the region here as well. EU West 2. And then let me just check that, yeah, Docker is running. So this authenticates with ECR so we can push our image up to our private repository. So if we go to infra again and do Terraform outputs to get the outputs, Terraform output, and then we do docker build -t, and then the name of our repo for our app. I'm going to go into the root of the project. So we need to be in the root of the project for this because we need to build our image and push it up to ECR. So I'm going to copy the ECR app URL for the app, and we'll do docker build -t paste, and then colon latest for the latest tag. And then we need to do --platform Linux /AMD64. So you only need to do this if you're using ARM processors. If you're using a 64-bit processor or an Intel processor, then you shouldn't need to do this. But because I'm using the ARM Mac M3 processor, I need to specify the platform so it can run on the target node. And then you can do, optionally, you can do --compress and then dot. This is going to build our image and tag it with the tag that links to our ECR repo. So we'll just wait for that to finish. Actually, while that finishes, or before that finishes, we can create a separate tab. And in that tab, we can run basically the same command. So we can copy the whole thing, except we're going to change it to or we're just going to change it to proxy to build our proxy image, and we're going to change this to our proxy URL tag. And then hit enter. That one builds a lot faster. So once it's built, we need to push it up. So we need to do docker push, and then the tag that we're going to push here. And push that. This will push the image up. Push the image up, and we're going to do the same for this image, which takes a bit longer to build. We just need to push the proxy image up, and we need to push the app image up. So the proxy is pushed. If we go into AWS and we go to ECR, we should see the proxy, and we should see the latest image pushed, and then we should see app pushed in a minute when that's built and pushed. So we just need to wait for that to finish. That should only take a few seconds. A few seconds more. And then after this is built and pushed, what we're going to do is we are going to modify our existing Kubernetes config to use EFS and to use these images. And we're going to remove Postgres because we're using RDS instead. We can actually go ahead and start doing that because I don't know how long this is going to take. It might take a while. So open up your code, and then inside the code, we're going to make some changes. So we are going to, first we can remove Postgres. We don't need this anymore. We can just comment it out, whatever you prefer. And then from customization.yaml, we're going to remove this. And then we're going to add a new file called storage class. And this is going to be a storage class for our EFS. So storage class.yaml, API version, storage.k8.io/v1, and then kind storage class, and then metadata name EFS-SC, which is EFS storage class, and then provisioner EFS.CSI.aws.com. I'll just get some water here. Okay, so our provisioner, and then parameters, and then provisioning mode, EFS AP, file system ID this we need to get from our Terraform. So somewhere we switch over to Terraform, we do Terraform output, and we take the EFS file system ID. Okay, and then directory perms colon 755. So that's the permissions. That means the owner can read and write and do everything, and the rest can read. I believe that's what it means. And then we'll do the base path colon, and then this is the base path where in the file system where everything is going to get added. So this is called dynamic provisioning. You can basically, this is optional. You can call this directory whatever you want, and it's useful if you have lots of different storage classes on the same EFS instance, because you can separate them all by their base path. Okay, so that is what we need for the storage class. Now we go into customization. We're going to add resources, storage class.yaml, which is the file we just added. And now we just need to make some changes. So before we continue, we'll just go back to the terminal. You can see that it's built this image now. So we'll copy the tag for the image that we built for the Docker image, and we'll do Docker push. We'll push that up. That takes a minute for it to push to the remote repository, but we'll let that continue while we carry on. So now we can go ahead and change our Django configuration here. So what we need to change is we need to change this persistent volume claim. So the persistent volume claim needs to be read write many, and we change storage class. So we need to add storage class name EFS SC. That's the storage class name. And then resources request storage. I'm going to reduce this to 5 gigabytes just for the sake of the cost. You don't need more than that for this particular app. And then image, we're going to change the image. So where it says containers image, here we have Django app latest, which was for our previous Minikube. We're going to change that to the image that we have just pushed. So we're going to change that to this image, including latest. So we'll copy that, we'll paste that there, and we need to delete this image pull policy never, because that was for just Minikube. We don't need that. Now we need to pull it from the remote ECR. And the same, or the next thing is also the Django Postgres DB host. We need to change that too. So we need to go and find our outputs from Terraform, DB instance address. We're going to change this to DB instance address. We're going to change Django Postgres to the new host of our RDS instance. And I think I changed this to Django project. So this is the name of the database in RDS. And then we are going to change the image for the proxy. So this is still pushing up, it's taking some time. We're going to change the image for the proxy. So that is this ECR proxy URL, but we need to remember to add the tag. So we'll find the proxy, change this to the ECR registry. So there's that colon latest. I'm going to delete the image pull policy here as never. And I think that's, for now, what we need to do for this file. We also need to go into customization. I think we change the password here to sample password 123. So that should match the password we configured inside our Terraform variables here. So you can see we have sample password 123. And that should be everything we need for the time being. Let's check that we've pushed our image up. Yes, so that's pushed. We go over to this and we refresh, and you can see that it's pushed the image up here. So the next thing we need to do is we are going to apply our Terraform change, or apply our Kubernetes changes. So we'll do kubectl apply -k, then / deploy, or just deploy /, and hit enter. And there you go, it should create the resources in Terraform. But we'll just continue for now. So it says that this is applied okay. We open up our dashboard, we go to the kind of home. You can see our deployments here. We got failed. So let's see what's failed. Okay, so it's probably failed on our Django maybe. So let's see. Let's change from kube system to default. Okay, Django. Oh, it says it's running. Okay, it didn't fail. It looks like it worked, okay. You can see it applied. So we know it can connect to RDS, because if it can't connect to RDS, then it won't be able to apply these migrations. We can see it can connect to EFS because it copied the stack files here. So that looks like that's all working. Maybe we did finish just in time, but obviously let me show you it working in action. Okay, so now what we need to do is go to services, and you need to copy this external endpoint here and go back to the config, and we need to set the allowed host. So if you come up to allowed hosts in line 73 and just replace that with this copied, but we're going to delete the port, and we are going to leave it just like that, and then go back to the terminal, apply it again, and what it will do is it will make the change, and it should shut down the old pod and start a new pod, which is what we wanted to do. Now, I did look at setting up a DNS name and HTTPS, but I didn't get around to finishing it yet. And also, as you can see, we've already kind of overrun on the live stream. So that one we can potentially cover in a future thing. It should be relatively straightforward to do by using an ingress service and setting it up, maybe using Helm to set up the cert manager or something like that. But we can look at adding HTTPS in another live stream in the future, or just a video or blog post or something. Okay, so this is restarted. If you go over to services and you click on your Django service endpoint here, you should see it loads our page. So we do test post, put my name here, some content, upload an image, and you can see it's all working as expected. So it's running in Kubernetes. Everything's working as expected. It should be storing this image in EFS. So if you were to go to the dashboard and you were to take a pod and you were to delete the pod, it will automatically recreate a new pod for us, and our image should still be accessible because the image is stored on a persistent volume as opposed to in the pod itself. So the other thing that you're going to want to know how to do is how to create a super user for the Django admin and stuff like that. So the way that you do that is you go to the pod and you're going to take the name of the pod and you're going to open up your terminal. You're going to type kubectl exec, which means execute, -it, which means interactive terminal, I think. And then the name of the pod and then sh, hit enter, and it will run this command on the pod. So now we're essentially SSH'd into the pod that's running, and we can type python manage.py create super user, and we can give it the name like Mark, and then mark@example.com, and then a password again, and now it's created. Now if we go back to the service that's running and just do /admin, log in with those details. Okay, so that's all working. That is it for the stream. I hope that you found this useful. Thank you so much if you attended, and especially if you stuck to the end, because I know this is quite tedious and you listened to me talking for an hour. And thank you so much, Brooke, for all your help in supporting to plan this and to promote this, and also doing all of the moderation of the comments. I really appreciate it. Now I'll just have a quick look through the comments here. So Anis, you asked, do you have an idea about Django DB migration on production, best practices to follow? I mean, how can we deploy Django V2? So basically the way that migrations work is it should handle itself in a sense. So what happens is we've deployed this now. If we were to make a change to the code base and that change involved a database migration, then we would create the migration as part of the code base, and then when we deploy the container, it should run the migration automatically because it's part of our startup script of our project. So if we go if we look in the project here, we should see app, or let's see, where do we, it's in scripts run. So this is the startup script that starts our container. So you can see it runs collect static and migrate. And this should be fine because every time you run a new container, if there is migrations to apply, it will apply them. If not, it will just skip. So you can actually see if you go to the latest pod that we restarted, it said no migrations to apply because they already were applied. So technically, anytime we make a change to the code base, anytime we deploy that, it should automatically apply the migration for you. So there shouldn't be an issue there. You could potentially have an issue where you, if you have a very large deployment and you have lots of pods running, then you might get a race condition issue where 2 pods try and run the migrations at exactly the same time. I haven't ran into any issues like that, and I usually deploy like this. I think that would be handled by Postgres, like it would lock the request for one and prevent it making the request twice. So I don't think there's anything special you need to do there. But if you did have a situation where you wanted to make sure that your migration is run only once per deployment, then you would have to do that as part of the deployment workflow. So here we have a deployment. We haven't really created a deployment workflow because we just kind of done it manually. But usually this would be deployed as on GitHub Actions or something as a process that runs. And you could do it as part of there. So you could manually run a specific pod on Kubernetes that executes the migrations before it pushes the config changes. So yeah, there's various different ways you can do it. It depends on your use case. I find this way works in like 99% of cases. This is the ideal approach, just to run the migrations as part of starting up the container. And I've never had any issue when running this in production. Okay, so do we have any other question? So try to make a video on deployment strategies like blues, green. Yeah, that's good suggestion. We'll keep that in mind when we're planning the content and stuff. I'm sure that will be useful for people to know. I was thinking of making more content around deployment workflows and things like that, because I find that that's something that lots of people find interesting. Thanks, Jason. Appreciate it. Thank you for the comment. And thank you, 4MJOV. I'm not sure if that's, I'm guessing that's not a real name, but thank you for the comment. I appreciate it. Glad that you found this useful. Obviously, if you do have follow-up comments or anything like that, you can leave them in the comments of the published video when we publish it, and I'll try and get back to them. I can't always get back to all the comments because we have quite a lot. But I really appreciate you joining the stream. But yeah, thanks so much, everyone. Really appreciate your time. I think we'll leave it there for now. And we do plan on doing another live stream. We're not sure when we're going to do it, but we do plan on doing it. And we'll obviously publish on our social media channels. Mayo, okay. Thank you, Mayo. No worries. Yeah, so we'll let you know via our social media channels when we do plan the next live stream, and we might we'll see how we decide what topic we do. Maybe we'll send a survey out, or maybe if you just let us know in some comments, or maybe I'll just choose something that feels like would be useful and that I know lots about. So thanks a lot, everyone. I'm going to leave it there. Really appreciate it, and yeah, hope you found this useful. And have a great day and weekend.